The F-14 Tomcat was designed for one thing and one thing only: to intercept state-of-the-art Soviet supersonic bombers before they could launch long-range missiles that could cripple the US Navy's largest aircraft carriers. Nothing in the US military's arsenal could handle this threat. A new generation of aircraft was needed that could fly up to Mach 2 to intercept these high-flying bombers, be capable of dogfighting at slower speeds when dealing with their fighter escorts, be rugged and strong enough to handle the extreme landings of carrier-based aircraft while carrying an enormous load of the most advanced air-to-air weapons ever created. And to top it all off, a powerful radar capable of guiding those weapons from an equivalent distance of New York to Boston. To do all this, the F-14 needed to be a shapeshifter, to adapt to the battlefield at a moment's notice. The swing wing of the F-14 allowed it to play two roles: a dogfighter and a high-speed interceptor. This is the insane engineering of the F-14 Tomcat. When the F-14 was proposed, variable sweep wings were nothing new. The Germans theorized the benefits of a plane capable of changing the angle of its wings back in World War II, and despite the expected complexity of the design, they followed through with a prototype design as part of the Emergency Fighter Program, a program created in a last-ditch attempt to turn the tides of the Allied aerial assaults that had crippled the Luftwaffe in 1944. This secretive plane, the Messerschmitt P-1101, was never completed. And in the final days of the war, as the US military marched towards Berlin, they stumbled across the innovative machine. Seeing the potential of the design, it was shipped back to the Bell factory in Buffalo, New York. 6 years later, the Bell X-5 rolled out of its hangar, bearing a striking resemblance to the spoils of war. However, the X-5 was a flawed aircraft. It would take decades of material science and aerodynamic advancements to incorporate a complex mechanism like this in a practical, operational combat aircraft. Variable sweep wings allow planes to adapt their aerodynamics on the go. When flying slower subsonic speeds, a lower sweep is preferable. It allows the plane to generate more lift with less drag. This is especially useful for a plane that needs to loiter in the sky for prolonged periods, protecting massive multi-billion-dollar aircraft carriers. But when needed, the F-14 can pin its proverbial ears back and accelerate to Mach 2.3, a highly desirable mechanism that is usually not included due to the added weight and the cost of maintenance. To make this practical, the designers of the F-14 would need to shave weight wherever possible, and they began with the F-14's wing box. The wing box is the foundation of an aircraft. It's the structural core upon which the entire aircraft is built. It connects the two wings together and resists the bending moment they generate, while supporting the entire weight of the aircraft through its connection to the fuselage. And the F-14 was going to be a heavy aircraft, the heaviest and most expensive fighter aircraft the US had ever developed, carrying two massive engines capable of pushing the plane to twice the speed of sound, 6 state-of-the-art air-to-air missiles that only the F-14 could use, 7 tons of fuel, a complex swing-wing mechanism, and a massive internal radar, which was the most powerful combat aircraft radar in service until the F-22 was introduced. Making the wing box as strong and light as possible was going to be vital for the F-14, and this was complicated even further by the need for a pivot connection for the outboard wings. Most wing boxes are constructed from aluminium, but Grumman made the decision early in the design process to manufacture the wing box of the F-14 from titanium, a notoriously difficult and expensive material to work with, but its benefits in strength-to-weight ratio were exactly what they needed. To work with this material, Grumman needed to develop a massive, one-of-its-kind titanium manufacturing facility that used a unique manufacturing process: electron beam welding. Electron beam welding, as the name would suggest, uses a focused beam of high-speed electrons to bombard a metal surface to generate heat with kinetic energy. This method was used because titanium is highly reactive with oxygen, and when heated, it becomes even more reactive. During the welding process, oxides form and contaminate the weld pool, resulting in an extremely weak weld. So, we need to weld titanium in a vacuum to ensure oxygen is not present. But that creates an issue because most welding techniques use combustion, which needs oxygen to generate the necessary heat. Electron beam welding solves that problem. This wing box was an engineering masterpiece, an incredibly strong and lightweight piece of structural engineering, reducing the weight of the wing box by about 15% in comparison to an aluminium wing box. And that was only because of this manufacturing technique. A titanium wing box that used bolted connections would have weighed almost 50% more. With this solid foundation, the engineers of the F-14 could start piling on the weight, starting with the engines. The F-14 needed extremely powerful engines with afterburners to be capable of reaching Mach 2.3, and to get up to those speeds, the plane would need to fly through subsonic, transonic, and supersonic flight regimes, which the plane needed to adapt to with more than just its variable wing sweep angle. Jet engines need subsonic air entering their compressors to function. Once the plane begins approaching supersonic speeds, the engine inlet needs to slow down the air before it reaches the engine. Grumman wanted to simplify the engine inlets as much as possible. Their experience with the F-14's predecessor, the F-111, taught them that curved inlets mounted on the fuselage needed to be avoided. The inlets of the F-14 are a simple box shape, which allowed the aerodynamicists at Grumman to simplify their analysis to a 2D problem, while moving away from the fuselage ensured they received as much high-quality, undisturbed air as possible. This is a cross-section of the F-14's inlet. After an initial fixed ramp set at 3 degrees, there are 3 computer-controlled compression ramps that vary with Mach number. The flight computer calculates their optimum position 40 times a second. At subsonic speeds, the ramps remained open. They could even over-collapse on takeoff and landing to allow even more air to get into the engines during the plane's lowest speed flight regime. However, at about 0.8 Mach, the throat area begins to narrow to slow down the incoming air, and continues to decrease the throat area to about 60% of its maximum area at Mach 2. Now, this may seem counterintuitive. At more familiar subsonic speeds, you likely know that fluid flow velocity increases through a narrowing channel like this, but the opposite is true for supersonic flow. These ramps are actually carefully positioning the shock waves that are forming in the inlet, and it's these shock waves that slow the air down to subsonic speeds. Another panel moves to adjust the height of this slot that leads to a bleed air door. This duct removes the slow-moving boundary layer air that forms on the compression ramps and exhausts it to the upper surface of the wing. Amazingly, these bleed air doors also helped future-proof the F-14, as the inlet was oversized for the original engines by about 10%. This bleed door removed some of that additional unnecessary airflow, but when more advanced engines were installed, the duct's opening was narrowed. This decision would prove to be an incredible foresight for the F-14, as we will see. Finally, the diffuser panel also actuates, with its angle increasing with speed. The airflow is subsonic at the exit of the compression ramps, so this diffuser can cause a larger decrease in fluid velocity through the expanding inlet area. The final half of the inlet consists of a constant area section where the inlet makes its final transition from its square shape to circular at the engine compressor fan entrance. To achieve this shape, the engines needed to be spaced far enough apart to avoid any intersection with the fuselage. However, if you look closely, you will notice there is actually more space than needed between the nacelle and the fuselage. The exact distance they were spaced was actually determined by the space needed to fit 2 Phoenix missiles side by side in the tunnel created between the 2 engine bays. This created a huge amount of area between the engines that could become a lifting body for the aircraft, decreasing the work the wings needed to do and decreasing the strength needed for the critical wing pivot, while also providing the additional space needed to house the mechanism that would control the wing sweep angle, but more on that later. There is some controversy surrounding the F-14. In 1984, Navy Secretary and Naval Flight Officer John F. Lehman stated that the F-14 was probably the worst airframe engine mismatch we have had in many years. The engines initially installed into the F-14 were simply not fit for purpose. The TF30 was an engine developed for the F-14's predecessor, the F-4D Missileer and the F-111. It was the world's first turbofan engine fitted with an afterburner, which provided the power needed to carry the incredibly heavy F-111. But both of these planes were bombers, which weren't expected to perform aerobatic stunts like the F-14. This was a problem because it was extremely susceptible to compressor stall, where certain maneuvers caused lower quality air to enter the engine and caused the aerofoils of the compressor to stall. This meant the compressor stopped pushing air into the combustion chamber and the engine lost power, sometimes flaming out dramatically. This issue killed many pilots, including the first death of a female fighter pilot in US military history, Cara Hultgreen. As she was approaching the USS Abraham Lincoln, she realized she was off the landing centerline and attempted to correct by yawing left. The nose of the F-14 then disrupted airflow into the left engine and caused a compressor stall. The F-14's engine placement made the situation even more dangerous, as the further the engine is from the plane's center, the more authority it has to yaw the plane in an engine-out situation. This increased the yaw even more and resulted in the left wing losing lift. This rolled the plane over so quickly that Cara could not eject on time. This asymmetric thrust issue could even put the F-14 into a deadly flat spin, as depicted in the crash that killed Goose in Top Gun. With accidents rising, the US Navy even had to implement special flat spin training for its pilots. Thankfully, the F-14 began to be upgraded with the superior F-110 engine in 1984, facilitated by some of that future-proofing of the engine inlet. This engine was developed specifically for fighter aircraft and featured inlet guide vanes that helped generate smooth, laminar flow for the compressor and prevent compressor stall. However, the TF30 continued to be used. You can easily tell the difference between the F-14s with the older TF30 engines and the newer F-110 engines by the engine outlet nozzle, which look entirely different. The F-110 was superior in every way imaginable. It had 32% higher thrust, which allowed it to take off from aircraft carriers without the need for afterburners, which decreased fuel consumption on takeoff considerably. The F-110 engine was so much more fuel efficient that the F-14Bs that came installed with it could stay in the air for 34% longer. And it was smaller and lighter than the TF30. The TF30 had 16 stages of compression, while the F-110 had just 12, making the engine shorter by nearly 1.4 meters, which required the afterburning section behind the turbine to be longer to fit into the F-14 airframe. This is what 20 years of engine development looks like. Between the two engines were two weapons rails, and when needed, the F-14 could be loaded with up to 6 of the most advanced air-to-air missiles ever created. This image looks like it's AI generated. There is just too much going on. But this was an actual configuration the F-14 could fly. These are 6 Phoenix missiles. The Phoenix missile was an extremely advanced air-to-air weapon designed specifically for defending the US Navy's fleet from supersonic bombers. However, it could only work in combination with the F-14's powerful radar. The AWG-9 radar installed into the F-14 had an output power of 10.2 kilowatts. In comparison, the F-4's radar had less than 10% of this power at 1 kilowatt, and is twice as powerful as the newer F-15's radar. This power output allowed the F-14 to identify and lock onto targets further than any other fighter aircraft in the US military's arsenal. When released, the solid rocket motors of the missile would accelerate it up to Mach 5 while climbing into the stratosphere. The Rocketdyne Mk47 motor that powered the Phoenix missile had a maximum burn time of 3 minutes, which is all it needed to reach its target at maximum range. Incredibly, the F-14's radar could not only lock onto a single target like most radar of the day, it could track 24 individual targets and help guide all 6 of the F-14's Phoenix missiles simultaneously in its track and scan mode. However, this did decrease the missile's chances of success over tracking a single target, especially if the targets were constantly changing direction and spread wide apart. In this track and scan mode, the radar would sweep the sky in front of it every 2 seconds. The velocity and position of the detected aircraft was then logged, and the tracking computer would create a virtual target that estimated the location of the target using the older data until the scan was repeated. In those 2 seconds, the radar could lose track of the target and the Phoenix missile would be on its own. However, if it was within 18 kilometers of its target, the Phoenix would have switched over to its own radar system, itself an expensive piece of equipment that was about to be disposed of. It guided the missile towards the target in its final moments, feeding data to the flight computer, which steered the missile with tail-mounted control surfaces. These control surfaces, mounted behind the missile's wings, lowered drag and offered extremely good maneuverability, allowing the missile to outmaneuver any bomber. During testing, the Phoenix missile even made 17 G turns successfully. Even the lightest, most agile fighter planes, like the F-16, are limited to 9 G maneuvers. However, the missile was rarely used outside of testing. It was a weapon designed for a Cold War scenario that never developed. Only global superpowers had technologies capable of targeting the US Navy's fleet at these distances, and thankfully, those technologies were never used. And even though the F-14 was capable of carrying 6 Phoenix missiles, it never would in regular operations, as this would put it over the landing weight limit of its aircraft carrier and force it to jettison a weapon with a $1.3 million price tag. Landing on an aircraft carrier with a plane this heavy was no easy feat. The F-14's landing hook had to be strong enough to arrest the plane's landing over an extremely short distance. The landing hook catches these arresting wires, which slowed down the aircraft with the help of hydraulic arresting gears below deck. But this did not always go according to plan. In 2002, the arresting hook of an F-14 broke off on landing. The plane dipped below the deck of an aircraft carrier with full afterburners on, at which point the pilot and radar intercept officer ejected. An investigation into the fractured arresting hook found that it had been embrittled by hydrogen after a refurbishment. The investigation deduced that sodium hydroxide that had been used to strip the aluminium coating of the arresting hook had generated enough hydrogen to embrittle the underlying steel. Taking off from the deck of an aircraft carrier is an equally adrenaline-pumping experience. When launching, the pilot will hold this switch to kneel the plane, which releases pressure from the nose landing gear shock strut. This lowers the nose landing gear by 14 inches and releases the lock on the launch bar, which can then be lowered into position by a member of the deck crew and connected to the C-shaped shuttle. These shuttles have been powered in a number of ways over the years. The majority of them are powered by a steam piston system, but the new Gerald R. Ford class carriers are now equipped with an electromagnetic rail system. These catapults are incredibly powerful and can accelerate the F-14 up to 290 kilometers per hour or 180 miles per hour in just 2 seconds. The fastest cars in the world can't even come close to that acceleration, with most struggling to hit 60 miles per hour in 2 seconds. This is obviously a dangerous operation, and one of the reasons the nose gear is compressed like this for launch is to create an automatic nose-up moment when the launch bar is released. When this happens, the stored energy in the strut pops the nose of the plane up and helps it to clear the deck safely. At this point in flight, the F-14's iconic swing wings are in the frontmost position, helping the plane generate as much lift on takeoff as possible. The wing sweep angle could be varied in flight from 20 degrees, used during takeoff and landings, to a maximum of 68 degrees, which was reached at 0.9 Mach. There was, however, a special setting of 78 degrees, which overlapped the wings and allowed the F-14 to be stowed more compactly on the aircraft carrier. The sweep angle was controlled automatically by the flight computer to optimize the plane's lift-to-drag ratio. This was particularly helpful in a dogfight where a pilot has enough to think about without considering the physics of transonic airflow, because wing sweep is designed to manage how supersonic airflow interacts with the wing. This is how it works. Take a straight wing for a small Cessna. Airflow over a wing perpendicular to the free stream air has one component, the chordwise flow, which is air that flows over the chord of the aerofoil. The chord is the imaginary line running from the leading edge to the trailing edge of an aerofoil. Chordwise flow is how the wing generates lift, and it does this by accelerating the air traveling over the aerofoil. However, because the air accelerates, It can hit supersonic speeds before the plane does. Different wings can accelerate this flow at different rates. The speed at which the flow over the wing achieves supersonic speed is called the critical Mach number, and generally we want to make that number as high as possible to achieve a better lift-to-drag ratio. The variable sweep wing allows this. Let's look at the airflow components over the F-14's wing at its lowest sweep angle, 20 degrees. Here, we can separate the airflow into two components, the chordwise flow, which is now offset by a 20-degree angle relative to the free stream, and the second component, the spanwise flow, which flows along the length of the wing and does not accelerate, and thus does not lower the critical Mach number. At lower speeds, where supersonic airflow is not a worry, you want as much of that airflow to be chordwise. We need that lift. This is especially true for a plane like the F-14. It's heavy and needs to land on extremely short runways in the middle of the ocean. The slower it can fly on approach, the better. However, as the speed of the plane begins to climb, we are generating more than enough lift thanks to the increased airspeed, and thus can afford to convert some of that airflow into spanwise flow. We do this by increasing the sweep angle. Once at supersonic speed, the primary concern is no longer critical Mach number, but with preventing the supersonic cone emanating from the nose of the aircraft from intersecting with the wings and lowering the lift-to-drag ratio. So, in theory, adding a swing wing has a lot of benefits, but it is rarely implemented due to the complexity and weight of the systems needed to make it happen. It needs a heavy-duty pivot capable of transferring the force of lift to the wing box. One way this can be simplified is by reducing the burden of lift on the wing. The total wing area was 52.5 square meters, but with the lifting body of the plane, the total lifting area was 93 square meters. This reduced the bending load on the pivot significantly. The control surfaces of the F-14 break from tradition in some ways. There are no ailerons to control the plane's roll. Instead, roll is controlled by these spoilers at lower speeds, but were locked when the swing wing reached an angle of 57 degrees at higher speeds, at which point the plane's roll was entirely controlled by the plane's horizontal tail, dubbed the taileron. This taileron used another wonder material of the era, boron fiber composites. Today, carbon fiber composites would be used, but during the development of the F-14, this new age material had not yet reached maturity. Boron fiber is produced by passing boron trichloride and hydrogen over a heated tungsten wire. So technically, they are boron-coated tungsten fibers, and they have excellent tensile strength, rivaling the highest quality carbon fibers, but are vastly more expensive. Boron fiber with epoxy resin composites were used in the taileron to reduce weight. The edges of the taileron were constructed from aluminium since they would experience more wear and tear. There were more problems that the swing wing created that the engineers needed to find solutions for. When the wings were retracted, a large portion of the trailing edge sat above the rear fuselage. To achieve a continuous contour behind the wing and the fuselage without any unaerodynamic gaps, an inflatable canvas bag was installed here. It was inflated with the engine bleed air when needed. Another problem the F-14 faced was its center of lift shifting backwards at supersonic speeds. This would cause the nose to dip downwards and require the plane to actuate the horizontal stabilizer to counteract it. This is something that affects all supersonic planes, but it was made even worse by the fact the entire wing actually shifted backwards as the plane gained speed. To avoid the drag needed to counteract this motion, the engineers of the F-14 fitted it with two extendable vanes on the leading edge of the wing glove. These were extended automatically by the flight computer. As the plane accelerated, the vanes would extend outwards and generate more lift ahead of the plane's center of gravity, counteracting the rearward movement of lift on the main wing. This lift forward of the center of gravity also helped the plane to perform 7.5 G turns at Mach 2, an incredible amount of aerodynamic pressure that really drives home how incredible that titanium wing box was. However, in practice, the vanes were rarely needed. While the F-14 was designed to fly up to Mach 2.4, the World War III scenario that would require it to never came to pass. The added weight and maintenance associated with these vanes were deemed unnecessary, so crews frequently removed the actuators and welded the vane door shut. In later versions of the F-14, the mechanism was simply removed in the design completely. requiring 30 to 60 hours of maintenance for every hour flown. The F-14 was ultimately retired in 2006 after 32 years of service. With the collapse of the Soviet Union and the advancement of interconnected stealth multi-role fighters like the F-35, the US Navy simply could not justify the price of this specialty aircraft. But it's precisely the specialty that makes it a wonder of engineering.